Anyway, our next speaker will be Sebastian. Sebastian, the stage is yours.
Thank you. Okay, so today I want to present you Rust on L4Re, integrating the systems language into the microkernel userland. And we're basically getting into two different worlds. One is Rust, and the other one is microkernels. And I expect half of you is into Rust and the other into microkernels. Not half by evenly split, but I am aware that some people are from the Rust world, others from the microkernel world. So I'm going to present you first what Rust is, then what L4 is, or no, the other way around. Then I'm going to tell you what's so hard about integrating this language into the L4Re world. And then I'm going to show you what currently works and how it looks like. And in the end, I'm going to give you an outlook about what will be done in the future. So first of all, what is L4Re? L4Re, or also called Fiasco, it has many names. It's basically a microkernel operating system built on a microkernel who is from the L4 family. It is really small itself, and which is also called a small trust computing base. So only around 10,000 lines of code, I think, run in kernel mode, and the rest is all in user space. Only scheduling in the kernel, the rest of all the policies is implemented in user space, be it paging, be it other resource management. It's all in user space. This is quite powerful, so obviously that also means drivers are in user space and all the things you expect from a proper microkernel system. L4 is capability based. Capabilities in this context mean that you have access to a certain kernel object from your task. A capability is always granted to a thread or task, and this object is local, so you can't just, it's basically numbers, so you index into this kernel table, but you can't just guess them because they're local to your task. And if you don't have a capability, you can't do anything. So if you don't have a capability to contact somebody else, you actually don't know that other party exists. Which is quite cool, because by default, a process is isolated. It can't do anything, not even memory management wouldn't be allowed to. Okay, so much about L4. Ah yes, I forgot. It obviously with these capabilities can do virtualization of resources and so on. And it features IPC mechanisms, obviously, because it's a microkernel. And since we're on a more complex microkernel with capabilities, there is our C and C++ bindings, though the C++ bindings are the ones you actually want to use, because it's a lot of basically protocol you would need to do for the IPC mechanisms to work. And C++ basically takes a lot of work from you by using C++ templates. You could use the C bindings as well, but then you need to do that all by hand. Oh yes, I forgot to mention that we have pthread compatibility, pthread libraries on L4 and basic POSIX APIs, just for the sake of completeness. So why Rust? I mean, obviously you have heard of Rust. I have not met anybody who hasn't. Rust is memory safe in most regards, so it does memory management on compile time. The programmer doesn't need to care about when is a variable free, at least not by the C terms to care about it. You prevent all these bugs like use after free, double free, and so on. It has strong, also called fearless concurrency, which permits you to write programs without data races. And you can also, to some extent, prevent deadlocks and so on. All these goodies are basically zero cost. So in the end, you don't pay for it. It's all done by the compiler during compile time. So we don't have any garbage collection or anything. all this you get with comparable performance to C++. So actually it's worthwhile exploring this. Let's have a look at the Rust ecosystem and the architecture, basically. First of all, there's a compiler called Rust C. Rust C is quite a normal compiler, basically. What comes on top is Cargo. Cargo is the project manager of the Rust project. It has a cargo.toml, which is a configuration file specifying dependencies and which files are actually used, and a few more bits. And on top, there's RustUp, which is the component installer. Now you think, okay, why are you talking about the component installer? That's more advertisement. Actually, it isn't. Because RustUp not only installs Rust C and Cargo, but it also manages components, so different standard libraries for different targets you want to compile for. Because Rust C itself is a cross-compiler, and you don't need anything special. If you have Rust C on your system, you automatically have a compiler for, let's say, ARM v6 or Spark, whatever. So with RustUp, you can just say, oh, please grab me the standard library for ARM v6, and you solve it. And this is obviously quite important for our use case, because if you install Rust by default, it won't have the L4Re standard library. But you can use RustUp to get it. Okay, so integration challenges. First of all, the standard library. Most of the standard library is using Unix or POSIX API, though there are it's split into many parts, and there's also Windows stuff. But despite Windows, it's actually all POSIX alike. And no, L4Re isn't POSIX. It has some compatibility layer, and we are actually using it. So I ordered the bunch of libraries you see listed there. They're all ordered to be used on L4Re, but internally it's using the POSIX API. As a side note, I should mention that the standard library is basically a facade to all these libraries you see listed there. This is quite powerful, because if you decide to not use the standard library because you don't want to have as much code in your program, because you have size constraints or whatever, then you can easily just select what you need. For instance, just the liballoc library for allocations. If I mention the word crate, you can substitute this in this talk with library, just for those who don't know the word crate. Another challenge is Cargo. BID, which is the build system of L4Re, does package management itself. It does dependency tracking, and it's quite convenient. But it's not convenient if you go for a language like Rust, which brings its own dependency management tool as well. Now you might think, okay, just ignore Cargo, integrate the Rust compiler, and you solve it. But it's not as easy, because the Rust project is built around this Cargo configuration. So if you want to have conditional compilation, for instance, called a feature in Rust, you actually want to have also a Cargo configuration file, because otherwise you would need to manually puzzle all these calls to the Rust compiler yourself when you port to L4Re. And therefore you actually want to use Cargo because it's all implemented there. You just somehow need to tell Cargo, please don't track dependencies, but do the rest for like conditional compilation, these features I just mentioned. So this one is still unsolved. And then I talked about IPC. So obviously we could just use a crate called bindgen and generate C bindings to be used in Rust, and then we have IPC working. You can do that, but it's cumbersome. What you actually want is leverage the Rust type system to generate all the code you need required to do useful message passing by the compiler during compile time, so not by hand. And this also is not done yet. Okay, the port and the compilation. Slide back. Oh, brilliant. So you stared at the JSON already. Rust itself, as I mentioned, is a cross-compiler. And it brings so-called target specifications with it. Even? Okay, what did I press? Yeah, brilliant, okay. So you might have seen some things you shouldn't see. But since you listened attentively, that's not a problem. Target specifications. So Rust needs only a handful of information about a target system, like n-units, pointer width, and so on. And you can specify this in a target specification. These are normally in a compiler itself, but Rust also allows so-called JSON target specifications. And these do, basically these do specify the same values, but can be passed dynamically because you can modify the JSON file. It's great for prototyping, what we also did. So we just tried and filled the JSON with values until it worked, which is nice, but it's JSON, it's not validated, and if you pass it to an arbitrary version of Rust, it most probably won't work. Given that Rust is released every 6 weeks, it's quite probable that your implementation won't work after a while, or not on a specific system with a specific Rust version. So it's better to integrate this. And the good news, Rust already ships L4Re target specification nowadays. Okay, so we looked at this slide already as well. The compilation process. I guess you're all familiar with that. So you can just invoke GCC and tell it to please output an executable in one go. But internally it will do assembly and will output an object file, and this object file will be linked by the linker, and then you have an executable. And the nice thing now is you can do all these steps by hand. In Rust, it's different. Rust, you can also, Rust C, you can just invoke and tell, please compile this to an executable. That works fine. But ripping that step apart doesn't work. Rust simply insists on calling the linker. I am aware that Rust supports emitting object files, but yeah, it really does only emit an object file. It doesn't provide you with all the information like an entry point and so on you would actually need for an executable. So this is not really useful. It's only useful for getting an object out of something which doesn't depend on anything else, which isn't like the reality works. Okay, so the conflict. Who does what? The idea. Does normally the linking. The process is really that the executable object files are generated out of C code, and then a custom linker command line is basically auto-generated by the build system. Custom means here we have a custom linker script, we have custom teardown and startup code, and so on. It also does dependency management, as I have pointed out various times. Since Rust C insists on calling the linker, we have now a problem. How can we actually get a binary out without Rust C actually knowing the exact linker command line for L4Re? The solution is somewhat problematic. We have a dirt hacker. Because since we haven't integrated cargo properly, and we haven't integrated the full command line of L4Re's linker invocation into Rust C, we currently just build a static library out of our program. So we just say, Rust C, please make a static library. Is there some problem with the attachment? Okay, so we have there's a dirt tag, which basically says, please compile this piece of code to a static library. But then you have to take care yourself that the linker will find the entry point, which usually boils down into exporting a C-compatible main function. And this is dirty because you don't have all the niceness of Rust, you don't have the proper dependency management of Rust, you don't have features, which are the conditional compilation of Rust. But at least you can write Rust and get a binary out of it, just with this intermediate step of a static library. Okay, so let's get a bit more. You see Makefile now, I hope. And the first 2 lines are just basically telling the build system where files are, so not too important. Then there's a normal target specification, which just tells Make how to call the binary. And then there's this nice source_rs variable. And this one does most of the magic, actually. It tells BID, this is a Rust file. Please handle it differently. And behind I listed all the source files of the application we want to build. It is quite interesting because Rust C, the compiler, only needs the first file to figure out which other files are part of the project. So it's in the C program we would need to list all the C files in the project. Here we only need the first, which is called main.rs traditionally. Okay, so Rust, a normal main function. It's just f in main, just a print, just a count, as you would expect it. For those who are not familiar with Rust, print ln is a macro. Macro, works roughly like the printf in C, just more type safe and with braces instead of percent. But yeah, what we actually have to do looks like this. First of all, we have to instruct the compiler to not mangle to mangle the name of the function, which obviously needs to be done because the type system of Rust is slightly more advanced than C's. Then we have to tell it to please use C calling conventions by saying storm C. And then in the function definition, declaration actually, you see the C types we have to use. Rust has different types, and so we have to use the C types at this place. But the rest looks the same. It didn't look half a year ago, but now it looks the same as the slide before because the standard library is now ported. Okay, this is what works at the moment. Let's have a look at what needs to be done. So obviously the linking step with the static library in between needs to go. For this to work, we have to somehow trick Cargo to integrate nicely into BID and BID to be nice to Cargo. Then we should figure out a really efficient way to handle IPC. I mentioned earlier that C++ does most of the magic which is required for IPC on L4. This is basically passing the object you want to send, for instance, as a template parameter. The compiler will take care of generating the code for you. Rust can do similar things with proc macros and so on. And it would be really great to have the same convenience in Rust. So, despite using bindgen for the simple C bindings, we should really invest more time into proper IPC bindings. And that's it. So I'm open to your questions now.
Is this project related at all to the Robbie-Gallia project for running a Rust microkernel user space around the SEL4 microkernel?
Okay, so the question is whether it's related to the SEL4 attempt to rewrite basically the user in Rust for Robbie-Gallia. And no, it's not. The thing is that L4 is just a family of microkernels. So even though they have roughly familiar semantics, they are completely different. So Robbie-Gallia has a project which tries to rewrite for this particular microkernel a new userland, whereas we try to just get efficient bindings on top of all the C Usernet which exists.
Have you tried writing on the Rust side programs using capabilities? Do you have some experience of what project capability side looks like in Rust? Because that's what you get once you bind L4Kernel to Rust.
Okay, so the question is whether I have used Rust to write programs using capabilities. Was that all?
Yeah.
No, because I haven't seen any project which runs on a microkernel with capabilities yet. So, for instance, I looked at Redux, but I haven't found any word about capabilities there, so I'm open to any pointers. More questions?
Do you think that the cargo project could benefit from trying to allow you to control how it links?
So the question is whether cargo could benefit from giving more freedom away to make the linker process more custom. Is that what you're asking?
Yeah.
So I would say so. I mean, other built systems have similar issues. There's actually a tracking issue for this on GitHub, and it's quite large. And because a lot of embedded people also want to do custom linking, and I personally would think yes, it would benefit cargo, but I don't know where to start to report problems there. So yeah, but I think it would be beneficial in general, yes, but for our niche case. So, but, okay, thank you.